Okay, some discussion for example 5-3. A typical floor plan in the private room areas of a hotel building is shown in the figure below. Design a typical B1 assuming the use of a select structural Douglas fir larch subjected to a dead load of 40 psf and live load of 40 psf under dry, moisture, and normal temperature conditions. Use wood density equals 35 pound per cubic feet. Compute the required bearing length. No need to use live load reduction. Okay, since this is a joist as indicated in the problem, and of course as we can also observe from the configuration, it is safe to assume that we're going to use a dimension number. Now this is a big thing because we know that the section properties, the reference design values rather are different for dimension number and timber, and so it is important to establish first if it is a dimension number or is it a timber. Now again, in this case, it is safe to assume that it is a dimension numbers since we're dealing with joist here. And I guess you could question, when should we assume otherwise? When should we assume that it is a timber? Then that would go for like girder G1 for the bigger beams, okay? So assuming that this is a dimension number, I already indicated here the properties for select structural DFL as shown here. And then I also wrote the given PD and PL equals 40 PSF, density 35, and then spacing the spacing of the joist is 16 inches. And then beam span is 18.5 for this side here. And then, oh, sorry about this one. Later I'll discuss the, I think, about the LU, there's a note, okay? Later we'll go back to that. Okay, let's first solve the loads. So we have here WDE, which is the dead load excluding the self-weight first because we do not know yet what the section is. So we have 40 times the tributary width, which is equal to the spacing, as you can imagine here. Okay? And then same thing with the live load, and so we have a total load of 106.667 pound per feet. And from that, we get our moment. And since this is, or assuming that this is a simply supported beam, we have 1/8 WL squared. And then we have 4,563 pound-feet. And then how should we look for the trial section? Well, as you can observe from our section properties, we have section modulus, which is more convenient to use rather than determining the I and C, right? Because it's just a single quantity. So let's solve for S, which is 36.5. And then from that, we find our trial section. Okay. So 36.5, how should we choose? Remember that the dimension number ranges from 2 to 4 inches thick. So we will deal with this section here. And then we need a section modulus of 36.5 cubic inches. Section modulus SXX, of course, because it is the strong axis bending, which is a very good assumption. And then 36, well, for 2 inch, we can use 2 by 14. We can also use in 3 around, what? 3 by 12, right? 36.5. 3 by 12, right? We can also use 4 by 10, okay? Which is 49.91. Now, from those choices, which should be the trial section? Even if we're checking the SX, of course, it would, the governing quantity would still be what? The weight of the beam. Because we want to find an economical beam. Okay, the SXX is just a criteria that we would know which is the appropriate beams. But for the economical nature of the beam, we need to look for the weight or consequently the area. And so by that, we can choose 2 by 14. Okay? Because it has an area of 19.88 as compared to 28 or 32. Okay? So 2 by 14, but that's just our trial section. We get the the exact dimensions, and then remember that when we solved for the dead load, we did not include the self-weight, and so we add the self-weight, which would put our total load into 111. And then consequently, the moment would be 4,770, and then the stress would be 1,304 times 10 cubed PSI. And then, this should be 1,304 PSI. Okay, and then we get the strength, FB prime. And so these are, I would not discuss this because by now you should know how to get or how to obtain these factors here. And then, as you can remember, we need to compute for CL. But from the problem, it's used as a typical floor plan. And then, since this is a floor, we can assume that there's a floor sheathing, right? There should be some kind of a diaphragm or floor for our area. And what is the implication of that? The beam is laterally braced all throughout the span. That's why I said that this is wrong, okay? The LU should be 0, which means that CL is equal to 1. Okay? Well, the solution is still correct. So CL is equal to 1, and then FB prime is equal to 1,553, which is higher than the stress. And therefore, our trial section is adequate. Okay? Since that was our first trial section, and we know that is the smallest beam in which S is passing, then we are sure that 2 by 14 is the most economical section, right? But just to show that it really is, so I just included a 3 by 8 here, the next smaller section, and we can see that it is still inadequate. But your solution could have stopped in this point because it was the first section that passes in section modulus, but the smallest one. And so you could have stopped here and your solution would be still complete. Okay, next. So we've checked bending, we proceed to shear. We'll go back to our section 2 by 14. And then we get our load, total load, 111. And then what would be the shear load? So 1/2 of the total load. And then FV equals 77.838. And then we compare that with the strength, FB prime, 180 PSI, it is adequate. But as you can remember from our discussion in shear, we said that we can use the shear force at the distance. But at this point, I just obtained the shear force from where? From the support. So how can that be justified? Well, if it passes or if it is adequate to the shear force at the support, then of course, it is also adequate into the distance, right? So it is easier to compute for the shear stress in the support. So if you want, you can check that first, and as in this case, and if it is adequate, then you can proceed with the next limit state. However, if it is inadequate, then that's the time that you can still check for the shear force in the distance. Well, you can also opt to directly check the shear at the distance. That's your choice. And still get the right conclusion that it is adequate. Next, we proceed with deflection. So I, it's just a formula, and then E prime adjusted. So, oops, that's not E mu. It should be E prime. Okay. So E prime 1.9 times 10 to the 6. And then we get our live load. As you can remember, two criteria for deflection, live load, and then total load. So for live load, we have 5 over 384 since this is uniformly distributed load. And then our limit is L over 360, and therefore it is adequate. And for the total load, so we need the dead load, which is still uniformly distributed load. So we have 0.277. You can also do ratio and proportion if you want. But we need K, right? So K factor. And we have our footnote here. As you have saw, in the solution we have K equals 0.5. And why is that the case? Because we have dry, right? Season or dry lumber used in dry service condition. And so 0.5, K equals 0.5, and total deflection is 0.393 compared to L over 240, which means it is still adequate. And then so we check the bending, shear, and bearing, it's adequate. And then for the last one, we are just required to compute for the bearing length. Okay, so for the bearing length, we use the reaction, and then we compute for the adjusted bearing strength, which is 625. And so we compute for the bearing length using reaction over the thickness times the adjusted bearing capacity. But I have a note here. I consider the exterior support, which means CB equals 1. If it was interior support, CB has a value other than 1, right? But why didn't I consider the interior support? Well, as you can remember from our previous chapter, CB is equal to LB plus 0.375 over LB. And you can expect that CB is greater than 1, right? Since this is a higher value, which means that CB projects, if we will use the interior support, it would give us a higher CB and therefore higher strength and therefore lower bearing length. But we need the more critical, and so we consider the exterior support in which CB is equal to 1. And so we have a required bearing length of 1.1. So our conclusion is use 2 by 14 dimension lumber with a bearing length of at least 1.1 inches. Or inch, if you may. Okay?